For a unity feedback system, G of S equals to 200 by S into S plus 8 and R of t equals to 2t. To reduce the steady state error by 5%, the new value of gain is, we know the steady state error ESS is given as limit S tends to 0 S into R of S by 1 plus G of S H of S. Here R of S is equals to 2 by S square, which is 2t, the Laplace transform of 2t. H of S equals to 1. So ESS equals to 2 divided by 1 plus limit S tends to 0 S G of S. This is 0, so this one. So which is 2 by kV. kV is nothing but limit S tends to 0 S G of S. So which is equals to 200 by 8, which is equals to 25. So ESS equals to 2 by 25, which is equals to 0.08. So if we reduce the steady state error by 5%, means the new steady state error is equals to, this is the new one after reducing, equals to ESS minus 5% means 5 by 100 into ESS, which is equals to 0.076. So now the new steady state error is given as 2 by limit S tends to 0 as k by S into S plus 8 is equals to 0.076. Means if we solve this equation, we will get k as 210.52, which is option B is correct. So the question is, match the least one with least two, referring to the 8085 microprocessor. Here least one, RP means written on positive, RPE means written on even parity, or Z means written on 0, or NC means written on carry. Here P means parity, CY means carry, Z means 0, S means sign. These are least 2 indicates the flag conditions, whereas least 1 are the instructions. So written on positive, positive means if sign bit is 0, it is going to be written, hence P is matched to the 4. Written on parity even means it is depending upon the condition, that is parity bit. So it is matched to Q is 1. Written on 0 means it checks the 0 flag, that is R is 3, and S is, that is written on carry means it checks the flag condition of carry, that is 2. So P4, Q1, R3, S2, hence option C is correct. Question is in the figure below, L1 equals to L2 equals to 2 Henries, R1 equals to R2 equals to 10 ohms, I0 equals to 5 amps. If RL equals to 1 ohm, find the drop across the RL at t equals to 0 plus, following the opening of the switch at t equals to 0. Assume steady state before switching. See, at t equals to 0 plus, we need to draw the diagram. So at t equals to 0 minus, at t equals to 0 minus, IL2 of 0 minus equals to 2.5 amps. IL1 of 0 minus also 2.5 amps, because the resistances R1 and R2 are equal. In the steady state condition, L1 and L2 acts as a short circuit. So I0 is equally divided between R1 and R2. So the magnitude of I0 is 5 amps. Hence, the IL2 of 0 minus is 2.5. IL1 of 0 minus equals to 2.5. So at t equals to 0 plus, IL2 of 0 plus equals to IL2 of 0 minus, which is equals to 2.5 amps. Hence, the voltage across the load resistor at T equal to 0 plus is equal to 2.5 volts, which is option C is correct.
In the solution of the differential equation, x plus y into dy by dx is equals to 2y. We can write this differential equation as dy by dx is equals to 2y minus x by y. Clearly we can say that the given differential equation is a homogeneous differential equation of order 1. Now, in order to solve the homogeneous differential equations, we have to take y is equals to vx. Now, if we differentiate, it will be dy by dx is equals to v plus x into dv by dx. Let us substitute all these values in equation 1. If we substitute, it will be v plus x into dv by dx is equals to 2vx minus x by vx. And if we simplify, it will be v by v minus 1 whole square into dv plus dx by x is equals to 0. It is nothing but v dv by v minus 1 whole square plus dx by x is equals to 0. That implies if we integrate, it will be v minus 1 whole square dv plus dx by x is equals to some 0. As we have added plus and 1 to the numerator, we'll simplify this. V minus 1 by v minus 1 whole square will be dv by v minus 1 plus dv by v minus 1 whole square dv plus dx by x integral is equals to 0. 1 by x dx, integral 1 by x dx is nothing but log x. And similarly, integration of dx by x square is nothing but minus 1 by x, which is minus 1 by v minus 1 plus integration of 1 by x is log x is equals to some constant. And if we simplify, it will be log of y minus x is equals to c plus x by y minus x. So which is option B.
For the circuit shown below, the resistance values and the inductance values are given. Find the admittance at a resonance. See, if we write the admittance function for this following network, we can write R plus j omega c plus 1 by RL plus j omega L. So at resonance, the imaginary term is going to be 0. That means R plus j omega c plus RL minus j omega L, RL square plus omega square L square. So if we make the imaginary term 0, we will get omega square L square equals to 1 by c minus R square. So omega square L square equals to L by c minus R square. So here now via admittance at resonance equals to R plus RL square plus omega square L square. We can substitute equation 1 in the equation 2, that is L by c minus R square. So if we substitute the given resistance and inductance values, we will get the admittance as 1.5 mho. That is option C is correct. For an 8-bit D2A converter having a reference voltage of 8 volts, the least significant 4 bits of the input are grounded and the most significant 4 bits are driven by 4-bit data from binary counter. The maximum obtainable peak-to-peak amplitude of a wave from at the output of the D2A converter. Here D2A converter is having 8 bits as input, means n equals to 8 bits. So the step size equals to, that means the resolution equals to the reference voltage divided by 2 power 8 minus 1, which is equals to approximately 31.37 millivolts. So the digital D2A converter having 8 inputs, that means 0 0 0, least significant 4 bits are zeros and upper 4 bits are ones, which is approximately in decimal equals to 240. So the analog output voltage V output equals to 240 into 31.37 millivolts, which is equals to 7.5 volts, which is option D is correct.